This is session B2, Einstein's Miracle Year, 1905. Last lecture we covered Planck's constant and quantum mechanics, and we completed that. Today we'll explore Einstein's Miracle Year, 1905. I'm going to be working pretty closely from my notes, which you have in front of you. But you don't need to read the notes. You can just listen and think. Read them if you want, but you don't need to. In 1905, Einstein was 25 years old. He was German-born, but had given up his citizenship and was now a Swiss citizen. His PhD dissertation was accepted in 1905, so he became a PhD. His thesis was on the determination of molecular dimensions. And in that year, he published 4 groundbreaking papers and will eventually get the Nobel Prize for the first one of them. Pretty good for a 25-year-old PhD student. Not a professor yet. Okay, his 4 papers, we call them by shorter names than the actual name of the publication. The first paper we call Photoelectric Effect. It actually dealt with multiple topics, all related to light, but we find it convenient to call it Photoelectric Effect. Most of this lecture will be about that paper and the photoelectric effect. Second paper we call Brownian Motion. He described the motion of small particles suspended in a liquid and explained what they meant for the size of molecules. He could not be sure that that was an explanation of Brownian motion, but we call it Brownian motion. Third paper, Special Relativity. And the fourth paper was the equivalence of matter and energy, E equals mc squared. These all have some relevance to quantum mechanics. The photoelectric effect more so than the others. We'll be talking about each of them, but we'll be talking more about the photoelectric effect than the others. We'll be talking about all of them in this lecture. His photoelectric paper, Einstein proposes a heuristic, so not a proof, that light consists of discrete energy quanta, and he uses that heuristic to explain several aspects of the generation of light and the interaction of light with matter that are inconsistent with Maxwell's equations and light being continuous waves, so inconsistent with classical physics. His paper consists of a number of sections. We're not going to discuss them all. He basically marshaled all the aspects of light that he considered inconsistent with classical physics and discussed them all in one paper. He was a master of thermodynamics and statistical physics and the kinetic theory of gases, and a lot of the paper has a lot of physics and math that we don't want to get into. We'll be able to get our results by looking at just one section of his paper. We're interested in Section 8 on the generation of cathode rays by illumination of solid bodies, which is called the photoelectric effect. I'm going to make one comment on Section 7, which is photoluminescence. It had been discovered that there are some materials where if you shine one wavelength of light on the material will re-emit a different wavelength of light. And when that happens, the re-emitted light is always a longer wavelength. And Einstein explains that in this paper, but we're going to study just the photoelectric effect. The point of his paper is that Einstein's going to propose that all of these areas in which light does not seem consistent with classical physics, they can all be explained if light consists of discrete energy quanta. We now call the photons. The paper doesn't say photons, and it was not Einstein who coined the word photons, but that's what we call them now. So if light consists of photons, and each photon is spatially localized, moves without dividing or spreading out, and is absorbed or generated only as a whole unit. Einstein says that classical continuous electromagnetic waves, as described by Maxwell's equations, that is time averaged values averaged over huge numbers of photons. And so we can't let the properties that we see classically of continuous electromagnetic waves, that's not the whole picture. And we can't let that's only part of our understanding. Now, what does it mean for a photon to be spatially localized? He didn't mean that a photon is at a point in space. He meant that it's not spread out over all of space. I don't know exactly the size of a photon, but we can think about it as on the order of its wavelength. It's one or two wavelengths near a point in space, but moving at the speed of light. Why are we going to focus on the photoelectric effect instead of the other aspects of his paper? It's pretty easy to visualize, it's relatively easy to understand, whereas some of the others are not. Thermodynamics is not. The photoelectric effect conveys everything we need to understand about photons for quantum mechanics. And we don't need to understand statistical mechanics and thermodynamics in order to understand the photoelectric effect. The photoelectric effect is similar to J.J. Thomson's setup where he discovered electrons. Einstein was working primarily from the results that the German physicist Philipp Lenard obtained in 1902. So I'm going to show you a setup that's idealized. It doesn't have some of the details that a physicist would need. So it's a glass vacuum tube, as was J.J. Thomson's setup. It has two metal it has a metal emitter and a metal collector, and they're connected to wires to an external circuit that can apply voltage between them and measure current between them. The emitter might be called a cathode, the collector might be called an anode. We'll call them emitter and collector. In this setup, there is no electrical heater heating up the emitter. We're not going to use high temperature to cause the emitter to emit electrons. Instead, there will be a beam of light that comes through a hole in the collector, and the beam of light will be perpendicular to the emitter. And under certain circumstances, the beam of light will cause the emitter to emit some electrons. And under the right circumstances, those will be collected by the collector and measured by the current meter. Now, it's important that the emitter consists of a single metal. It could be silver, it could be sodium, potassium, lithium. So it's either made of that or it's completely coated by that metal. For simplicity, we're going to assume that the collector is always the same metal. We'll run different experimental runs where we'll change the metal, but the collector will always be the same metal as the emitter. This is not necessary, but it simplifies the physics, and we don't need to understand the complications, so we'll use the simple case. Now, it's important that there be no oxide on the emitter and collector, so they have to be chemically etched in the vacuum tube to get rid of the oxide so that they're chemically pure metals. The light source, we want it to be monochromatic. We will use different colors of light on different runs. Some red, some green, some blue, some ultraviolet. But it turns out important to our ability to understand the photoelectric effect that the light source be a single wavelength at a time or a very small range of wavelengths at a time. We can achieve this with filters to block all but a certain wavelength, or we could split the light with a diffraction grating. So different runs will use different colors of light, including ultraviolet. During a particular run, we will set the light intensity to some value, and we want it to be constant during the run. So it needs to be settable over a wide range of intensities from dim to bright, but during a run it needs to be constant, and we need to be able to measure what the intensity is. Now, because we want bright ultraviolet, we can't really use sunlight. The amount of ultraviolet that comes through our atmosphere is not very bright, not very intense. So what they used as a source of light was electric arcs, electric discharge arcs, arc lamps. That can be very bright, and it includes lots of ultraviolet. And so that's what they used for the source of light. The light will be perpendicular to the emitter, and okay. So that's the setup. We were going to have different experimental runs for different combinations of emitter and collector metal. Silver, sodium, potassium, lithium, whatever we want, but metals. Different light frequencies, different visible light frequencies, different ultraviolet light frequencies or wavelengths. Different light intensity. And also different voltage on the collector relative to the emitter. We will see later why we want to do that. So that collector to emitter voltage, VCE, we will vary that, and we will talk about that. It turns out physically that each metal takes its own specific amount of energy, called its work function, W, to remove a free conduction electron, so not a valence electron bound to a given atom, but a conduction electron that happens to be near the surface of the metal. So it takes the amount of energy called the work function to remove an electron from the interior surface to the exterior surface outside the metal, so to emit the electron. Then the electron's just sitting outside the metal, and if we do the right things, the collector can capture it and measure it. Now, I'm going to tell you that the work function for sodium is 2.36 electron volts. In the last lecture, we talked about how big an electron volt is and what that means for visible light. We'll talk about that more in this lecture. Silver, the work function is around 4.5 electron volts, so more than sodium. We'll see later why we pick these two metals as good examples for the photoelectric effect. Let's reason from classical physics and try to make some predictions about electron emission in different kind of experimental runs that we could do. See if you can make some predictions about what we should expect in the experiments. So if you want, pause the video, think about it, write down your predictions, and then I'll go over some predictions. This is a possible time to take a break. We need to know a little physics, but not a lot of physics. The first thing is that light intensity is transmitted power per unit area, which is energy per unit time per unit area. We will require that the intensity is uniform over the illuminated area A at the emitter. Now, we'll assume that a free conduction electron that's at the surface inside the metal, at the surface of the emitter inside the metal, that it can absorb energy from the illuminated light over some effective surface target area around the electron, and that area is independent of the light intensity. Then the electron will absorb energy continuously at a rate of the intensity I times that area, that much energy per unit time, until it gets emitted. So the electron will absorb an amount of energy W, the work function, in a time t that is the work function divided by the intensity times the effective area that the electron can absorb over. And when it's absorbed that much energy in that amount of time, then it'll be emitted. This is an assumption. We want to see if that's how it really behaves. So we'll make our first prediction. Prediction number 1. When we turn on the light source, the first electrons will get emitted at time t, because it takes that long for the electron to absorb that light intensity over that area enough to get enough energy to be the work function. So that's the time delay. And then at that time delay, we'll start to see electrons. Lower light intensity will have a longer delay. before the first electrons are emitted. Let's assume that we always have some amount n surface free electrons, free conduction electrons per unit area. There are always that many free conduction electrons sitting at the emitter surface, independent of the light intensity. When one gets emitted, another one takes its place. There's an endless sea of them. We don't run out of them because we have an electrical circuit. So, when the collector collects an electron, it will get returned to the emitter. So we don't run out of electrons. The number of electrons emitted per unit time is going to be the number that are at the surface per unit area times the area divided by the time it takes for them to get emitted. So N times area A times the intensity I times the effective absorption area sigma divided by the work function. And if all of those that's the number emitted. If they all get collected, because we put a positive collector to emitter voltage to attract them, then the magnitude of the electric current is just going to be the charge on the electron times that quantity. So we can make another prediction. The electrical current will be linearly proportional to the light intensity I when all the electrons get collected. We'll see if that's true. Now, it might happen that electrons absorb more energy than the work function from the light before they get emitted. And then when they get emitted into the vacuum, they'll get emitted with positive kinetic energy. K equals the amount of energy they absorb minus the work function energy. We'd like to measure this and see if it occurs. It'll become pretty important. We can do that if we apply a negative collector-emitter voltage. Then we're making it harder for those emitted electrons to get collected. We're blocking some. So this is a blocking voltage or a stopping voltage equal to the magnitude of that negative voltage. Electrons then will only get collected if the energy that they have when they get the energy that they absorb is larger than the work function plus the blocking voltage. Then they'll get collected. And they'll get blocked if that's not true. So we can make another prediction. If an electron gets collected, if we have some collector-emitter voltage, the electrons that get collected and produce the electrical current, they're still going to be proportional to the light intensity. If some get blocked, the amount will be less. If they all get blocked, the amount will be 0, but it'll still be proportional to the light intensity. We'd like to see if that's true. We can make another prediction. The electric field at the surface of the emitter that's due to the light wave, that electric field increases with the square root of the light intensity. So I'm not going to explain why, but we might think that the electron kinetic energy and the collector-emitter voltage required to block electrical current, that those should increase with the light intensity. Because maybe should increase with the electric field intensity. We'll see if that's true. Everything we've just said did not depend on the wavelength or frequency of the light source. So if we have a correct understanding, then we can make another prediction. The emission of electrons, the time delay for emission, the electron kinetic energy, and the electrical current, those should be independent of the light wavelength and frequency, as long as the light intensity is not super small. We'll see if that's true. So Lenard did the experiment in 1902 and found some things. He determined that the emission rays were similar to cathode rays, and we now know that they are in fact electrons. But he showed that. He had a very sophisticated setup for doing that, which we're not explaining. He found that emission of electrons required a minimum frequency of light. Well, okay. That already disproves one of our predictions. He found that the maximum kinetic energy of the electrons, it was independent of the light intensity, but it was greater for shorter wavelengths of light. Now, his experiments did not produce nice graphs, as far as I know. But let's compare our predictions against Lenard's results. We thought that the low light intensity would have a long delay before the first electrons are emitted, because the electron was absorbing light slowly but surely. And Lenard's results say this is false. He didn't find any delay. We now know that when electrons are emitted, they begin to be emitted within 1 nanosecond of the light turning on, even at the lowest intensity you could want to run the experiment with. So that's a false classical prediction. Let's look at the second one. The electrical current will be linearly proportional to the light intensity for any given collector-emitter voltage. This is true, but when we look at the final row, we'll see an interesting result. So one classical result was true. Let's look at the next one. The electron kinetic energy and the collector-emitter voltage required to block the current should increase with the light intensity because the electrical field intensity increases. This was proven to be false. The electron maximum kinetic energy was independent of light intensity, and we can now verify this over a range of intensities of at least 10 million. We can use lasers now. They didn't have lasers back then, so we can get pretty high intensities. The electric arc lamps were very high, very bright light, very high intensity, but when you filter down to a narrow wavelength, it's not as intense as a laser can be. So here's another. So this is the second classical prediction that was proven false. Here's another one. The emission of electrons, the time delay for emission, the electron kinetic energy and electrical current will be independent of light wavelength and frequency if the light intensity is high enough. This is false, or mostly false. A given emitter metal has a minimum light frequency, F0, called its characteristic cutoff frequency, required to cause emission and current. Different for different metals, but for any given metal, it's always the same. There's no delay, even at low intensity. We talked about that. The electron kinetic energy does depend on the light wavelength and frequency, and we're going to talk about that a lot. So here's another classical prediction that the photoelectric effect proves false. This is a possible time to take a break. So Einstein has good reason to say, well, look, classical physics is not successfully explaining these things. The photoelectric effect is not consistent with the expectations from classical physics. And Einstein was bold enough to say, here's how we fix that. And his fix is very bold. Einstein says, Planck's proposal that the blackbody radiation cavity modes are quantized in discrete light energy quanta, that we call photons now, with energy E equals hf. Planck was cautious and said, well, I can only say this applies to these blackbody radiation cavity modes. Einstein says, no, this also applies to the photoelectric effect. And in blackbody radiation, we were looking at the cavity emitting cavity modes. Here we're looking at the emitter absorbing light. But that light gets emitted by other matter. It gets emitted by our arc lamp. So Einstein's bold statement is that E equals hf applies not only to the light beam and the photoelectric effect, but to all light and all electromagnetic waves. And that is now known to be true. Pretty bold. He's young, he's 25. He's early in his career, although he's bold. I mean, for a guy who wants to get a professorship somewhere, this is a pretty bold statement that could possibly be false, but in fact turns out to be quite true. He says these energy quanta that we now call photons, they're pretty localized in space. They're not distributed over all space. They're not spread out over all space. They're localized in space when they're emitted, when they're moving at the speed of light, and when they get absorbed. They get absorbed in one place. He says, the absorption of light occurs by a single photon being fully absorbed by a single electron at the metal surface. We'll say that in all interactions between electromagnetic waves and matter, photons are absorbed or emitted as individual, indivisible units. When the frequency of the light is smaller than the cutoff frequency for a particular metal, a single photon does not transfer enough energy for the electron to overcome the metal's work function. But we should look at that a little more. and think about what happens. So on the left here I'm showing, so the vertical axis is energy level for electrons. This horizontal line is meant to show that's the energy that an electron would have if it was unbound, sitting in the vacuum and not moving. It could be close to the emitter, it could be far from the emitter. That's the unbound, no motion energy of the electron. But the electrons in the metal, they don't all voluntarily come spilling out all the time. They stay in the metal because they're bound. They're bound in the metal. So they don't always leak out and spread around the vacuum. They're bound in the metal, and some of the electrons, they're tightly bound to individual atoms and we call them valence electrons. But this is a metal, and metals conduct, and the electrons that we're going to show here, they're bound in the metal, but they're not bound tightly to any given atom. They're free to move around the metal. They're in the conduction band. So the freely moving conduction electrons in the body of the metal, but also right at the surface. The amount of energy, the energy difference between vacuum and these conduction band electrons is called the work function W for that metal. Now, what might happen if we shine light on it, but the light is a low frequency, a small energy, an energy smaller than the work function? Lenard found that this did not cause emission, but let's look at, we'll think about this, what might happen. So this conduction band electron at the surface, it could absorb a photon and jump up to this energy level. And while it's at that energy level, it could absorb another photon and jump up to this level. And then jump up to this level, and then jump up to this level. And now it has a high enough energy that it could leak out of the metal, get emitted. But this didn't seem to happen according to Lenard's results. Why didn't it happen? So I don't actually know the answer for sodium or silver, but there's two answers we could conceive of, and I'm sure one or both of them are correct. One possibility is that at some energy levels in the metal, there are no states. And so an electron could be in this state, it could be in this state, but here there's no states. And so it can't absorb that photon because there's no state there. And so it gets blocked from making it to the top. Another possibility is the electron absorbs this photon and it's at this energy level, but before the next photon comes along, it drops back down. It either re-emits that photon or it interacts with the other electrons and atoms in the material and emits thermal energy and drops back down. So if it drops back down too quickly, then it's not going to make it to the top here. Now with modern lasers, you could do this experiment with very bright intensities. And if you get the intensity and the frequency of the light correct, you probably can get an electron to absorb a photon, sit in an intermediate state, and the intensity is so high, maybe you can get the second photon to emit it. But this was not available in 1902 at all. And I don't actually know what would happen if we did the experiment with modern lasers. Let's look at energies, photon energies now that are enough to cause emission. On the left here, we're shining light with exactly the energy of the work function. And so an electron absorbs one photon, it jumps up to energy here, it has enough to leave the metal, and it can be collected. So that's energy HF, exactly equal to the work function. But if we use smaller wavelength, higher frequency light, the electron could absorb an amount of energy E equals HF that's greater than the work function. And in that case, when it leaves the metal, it has non-zero kinetic energy in the vacuum. Kinetic energy equal to E minus W or HF minus W. And we want to conduct experiments to see this kinetic energy as a function of light frequency. Lenard's experiments did not exactly show this. He didn't have graphs of this, but Einstein said, this is really important. This is the whole effect. This is the proof. You want to be able to graph kinetic energy of the electron versus frequency. Einstein said that, not in those words, in his paper. So his paper proposed measuring the electron kinetic energy versus the light frequency by using different blocking voltages. Now, if you ever want to read this paper, you won't ever find Planck's constant H in it because Einstein used R over N times beta instead of H, and physicists used nu for frequency instead of F, and Einstein used P for the work function instead of W, so kinetic energy is R over N beta, which is H, times nu, which is F, minus P, which is the work function. This is a possible time to take a break. Now, as important as we now know this photoelectric effect to be, and how correct we know Einstein's light quanta to be, photons to be, his idea was universally rejected by physicists. Lenard rejected it, Planck rejected it, Niels Bohr rejected it. In a few years, Planck and others in Germany will recommend Einstein to be a member of the Prussian Academy of Sciences. And the write-up that they included with their recommendation basically said they're recommending him in spite of his ideas about quanta and photons. So not because of it. In 1914, they still believed it was wrong and it was a mistake, but Einstein was a pretty smart guy. He had made a lot of good contributions. Everybody makes mistakes. These photon ideas are just a mistake. We'll get over it. But physicist Millikan used Einstein's suggestion, and he produced better photoelectric effect experimental results in 1914 and 1919 with nice graphs that we will look at. And he eventually will win the Nobel Prize for that work. And Einstein in 1921 will win the Nobel Prize for the photoelectric effect. But in 1914, physicists thought he got it wrong. Now, why did they think he got it wrong? He laid out a bunch of arguments, he explained them all. The thing is, they didn't necessarily disagree with his list of things that couldn't be explained by classical physics. But how could these individual quanta of light possibly agree with electromagnetic waves, which all these scientists knew was true? There were plenty of experiments about electromagnetic waves. It's what they learned as students. They understood electromagnetic waves. They understood Maxwell's equations. They believed it completely. There was no way to understand quanta or photons, how that could possibly be consistent with Maxwell's equations. Einstein was bold enough to say, yeah, there's a disagreement there, but you can't ignore these phenomena and these results. We got to do more work to figure out how to make them, how to understand them. But he was alone in the desert for, I guess, 9 years. Nobody agreeing with him, but it didn't stop him from saying, well, I laid out my ideas. I made a suggestion. Experimentally go test it. And that's what Millikan did. Millikan ran tests with different metals. I'm only showing silver and sodium, but he also used lithium. He used different light frequencies, and he did it with his results, I'm sure, were not continuous like this. He used specific light frequencies, so his graphs would be dots, not a line. How could he measure the maximum kinetic energy of an emitted electron? Well, by applying a negative collector to emitter voltage, you can stop all the electrons that don't have a kinetic energy equal to the stopping voltage or higher. So you can do multiple runs at different stopping potentials, and then see what your see if you do or don't collect any electrons. And if you have a frequency and you have a stopping potential and you do collect some electrons, you take the frequency and the stopping potential and you put a dot there. So what I'm showing as lines would be just some dots. You do enough runs, you could see that, well, it would be a line. It would be a line that would end at a cutoff frequency for that particular metal. A lower cutoff frequency for sodium than silver. You could take the dots or the line, you can calculate the slope. Millikan did that, and the slope was agreed with Planck's constant h, just like Einstein said it would. Now, if Lenard's results in 1905 had been this granular, then other scientists could see, look, cutoff frequency, look, line, look, slope. Hey, the slope is Planck's constant. Something's going on here. But Lenard and Einstein didn't have this in 1905. Einstein just reasoned out and knew that it had to be this way, and then Millikan confirmed it in 1914. I said that sodium's work function is 2.36 electron volts. You know from the last lecture how to turn that into a frequency, and you can look in charts on like Wikipedia and whatever, and you'll see that that's borderline green cyan light, so visible. Higher frequencies than this will cause emission. So blue will, violet will, ultraviolet will. Lower frequencies than this will not. So yellow will not, orange will not, red will not. I said that silver's work function is about 4.5 electron volts. You should be able to use the results of last week's lecture to tell that, well, that's not even visible at all. Visible ends at, I think it was 3.1 electron volts. So this is ultraviolet light, which is why we needed ultraviolet light. We couldn't just use visible light. Now, in reality, now that we know this, the photoelectric effect is the good way of determining what the work function is for a particular metal. Now we have it, now we know that. There's other ways, less good, more confusing. Now, Einstein got the Nobel Prize in 1921 for his services to theoretical physics, and especially for his discovery of the law of photoelectric effect, which, remember, until 1914, other physicists thought he got totally wrong, but in 1921 they had come around. There's no mention in here of special relativity, which Einstein did in 1905, or general relativity, which Einstein did in 1916. Those were absolutely revolutionary, but actually, the fact that light consists of quanta, of photons, that's revolutionary too. So you could say that for his services to theoretical physics includes special relativity and general relativity, but the Nobel Prize Committee was not about to be so bold as to say that special relativity was true and proven, or say anything about general relativity in 1921. Okay. I wanted to say one thing about the sodium. The green cyan light that is required to cause emission in sodium, don't confuse that with the color, the yellow-orange color of sodium vapor lamps, street lamps. It's a different physical effect. It has nothing to do with they have nothing to do with one another. Lamps are sodium vapor. This work function is specific to a solid metal. There are different effects. Okay, jumping ahead. Beyond Einstein's paper. Large collections of photons produce electromagnetic wave behavior. A photon is not simply a classical particle like a billiard ball. Somehow, each photon has particle and wave aspects, because somehow when you get a massive collection of photons together, they implement wave behavior. This is confusing to understand. It's hard to believe. It's hard to explain. But it is part of the essence of quantum mechanics and why we need quantum mechanics. And we will be talking about it more in future lectures. I want to say a few words about Philipp Lenard. He was a German physicist, older than Einstein. He was anti-Semitic. He was nationalistic, German nationalist. Under the Nazis, he was pro-Nazi. It was Philipp Lenard who labeled Einstein's physics as Jewish physics, as opposed to good German physics. Not the photoelectric effect, which Lenard had come around to accept as the explanation. But special relativity and general relativity, Philipp Lenard labeled them as Jewish physics, and the Nazis labeled them as Jewish physics. Just something to know about Philipp Lenard. This is a possible time to take a break. The second paper we'll talk about is Brownian motion. It's not super related to quantum mechanics, but we'll talk about it briefly. And so you've probably all seen some aspect of Brownian motion. If you've looked in, a sunbeam is so bright that it illuminates dust particles, and you see them moving around. But when you see that, there's air currents. It also happens in liquids, in water. If you look in a microscope with a bright light, you could see dust particles or pollen grains suspended in the liquid. Now, if you make the liquid static, not move, and you watch, I've never done the experiment, but I'm told that you will see that even though the liquid as a whole has no currents, the dust or the pollen grain will move within the liquid. It has kind of a random walk within the liquid. You could say, okay, that's interesting, don't really care, moving on. But Einstein said, well, let's record that motion. They didn't have video cameras, and a photographic camera would do no good. So what Einstein said is, watch for a while and draw what you see. Oops. Particle starts here, it moves in this direction, it moves about this far, and then it changes direction and goes that far, and then this and this. He said, record all that, and he produced a formula based on statistics, probability. He said, record those lengths and directions of the random walk. Use his formula and you'll get a quantity called the diffusion constant, D, for that liquid. Not for the pollen grain, but for the liquid. And then he gave another formula. It said, from that, here's how to calculate Avogadro's number for the liquid. Now, anyone who's taken, well, chemists will remember, and some of you who've taken chemistry will remember what Avogadro's number is. It's the number of molecules per mole for a particular material. Well, what's that? Some physical laws, some chemical laws. So a mole is the amount of material that we would use if we wanted to talk about chemical formulas for chemical reactions. I don't want to discuss it in too much detail. I might have bitten off a little more than I can chew here. I don't want to confuse you more. So those of you who know what Avogadro's number is, he gave a formula for how to produce Avogadro's number from the diffusion constant. And then he did not say, because physicists then just knew, but we can use Avogadro's number to calculate this approximate size of the liquid's molecules. We're not going to take Brownian motion data and derive Avogadro's number, but I wonder if you can take what we now know to be the value for Avogadro's number, 6 times 10 to the 23 molecules per mole. Take that and other information about water. Can you calculate the size of water molecules, approximately? See if you can do that. You can find information about water on the Wikipedia page for water. So water's molecular weight is 18 grams per mole. If you don't know what grams are and you don't know what moles are, don't worry about it. Don't worry about this section. Water's density is 1 gram per cubic centimeter. We could calculate the approximate volume of a water molecule. 18 grams per mole divided by 1 gram per cubic centimeter times Avogadro's number, 6 by 10 to the 23 molecules per mole. Grams will cancel, per mole will cancel, the per cubic centimeter will go up to the numerator. 18 divided by 6 will give us 3 by 10 to the minus 3 cubic centimeters. Now, if we think about that volume as a cube, we can find out the linear size. Just take the cube root, and we find that's 3 angstroms. 3 by 10 to the minus 8 centimeters, 3 by 10 to the minus 10 meters, 3 angstroms. And we now know that the size of an atom is about an angstrom, and a water molecule is 3 atoms, and it's longer in one direction than the others. And so this is pretty good agreement, considering we didn't have to do much work. So Einstein's point was we can look at pollen grains in a liquid like water, and we can get a value for Avogadro's number, and therefore the approximate size of water molecules or liquid molecules. Now, why do we care for quantum mechanics? We kind of don't. I mean, it's another step toward physicists believing that they had proven that matter consists of atoms. They have lots of evidence, what we would call proof, but it was such an important, bold step that they wanted all the proof they could get, and this is another step in that proof. But was this a groundbreaking paper? He had published his PhD thesis, which was a different approach to finding molecular sizes. That used physical properties of dilute solutions, but not looking through a microscope. Physical properties of the solutions. And there were other theories that would give Avogadro's number. You could use the properties of gases and get Avogadro's number, and they all agreed generally, order of magnitude anyway. But liquids were not as well understood physically as gases in terms of the behavior of atoms and molecules. So there wasn't a kinetic theory of liquids. But what was unique about this approach was you could actually look in a microscope and record things and crank his equations and get an estimate for the size of molecules. All the other things, there were theories for them, but it wasn't, you would measure the pressure, the volume, the temperature, but you didn't look at anything in a microscope. So we could consider it groundbreaking in that you actually see something happening. Now, I want to have a comment about water. Water is unique, or very darn near unique. For almost all liquids, when they solidify into a solid, the solid is denser than the liquid. Water is the only material I know where the solid is less dense than the liquid. Ice floats on water. I know there are supposedly explanations of why this is true from a physics standpoint and from a physical chemistry standpoint. I don't understand that. It's not exactly a quantum mechanics problem, but it actually is important to Earth and life on Earth that water has this property. Ice floats on top of a liquid, on top of a river, a stream, a lake, and then the ice insulates the water from the colder air. So it slows down the freezing of the lake or the ocean. If ice was denser than water, it would sink, and then there would be continuous opportunity for the air to cool the liquid, and larger lakes would freeze in cold winters, and in ice ages, even the biggest lakes would probably freeze solid and kill all the life in them. You know, the fish that survive the winter, the animals that bury themselves in the ground under the lake, they would probably all be killed in an ice age. The oceans would be affected too. The Arctic oceans, the southern polar ocean, Arctic seas, they could potentially have frozen over in an ice age. But that didn't happen. They didn't freeze deep. So water is unique, and life on Earth benefits from it. This is a possible time to take a break. The third and fourth papers, the third paper we call Special Relativity. Einstein called on the electrodynamics of moving bodies. And the fourth paper is he used inertia depending on energy in his paper title. I don't remember the exact title, but we think of it now as the E equals mc squared paper that deals with the equivalence of mass and energy. I'm mostly going to talk about special relativity. I may have a few comments about the E equals mc squared paper. These do impact quantum mechanics, but not necessarily in the way that the paper was going for. So, what motivated this special relativity paper on the electrodynamics of moving bodies? Maxwell's equations for electric and magnetic fields in the mid-1800s, physicists believed them completely. They were proven correct endlessly. You could manipulate Maxwell's equations and it would produce electromagnetic waves. It would explain how electromagnetic waves could propagate in space, including in vacuum. And pretty surprisingly, it produced a speed for the electromagnetic waves, a speed independent of wavelength, the speed that they must travel and will travel in vacuum. And surprisingly or shockingly, that speed agreed with the known measured speed of light, which had first been measured in Newton's time. Nobody previously knew what light was. There was a science of optics, and they knew a lot about light, but they didn't know what light was. But when the speed of electromagnetic wave propagation matched the speed of light, physicists said light must be an electromagnetic wave, just of a high frequency, short wavelength. And we now know that to be true. But there's a problem. The speed of light that comes out of Maxwell's equations, it has a value, and there's nothing in that derivation that says what reference frame that speed of light is relative to. It's just, this is the speed of electromagnetic propagation. This is the speed of light. Well, what if the light source is moving toward us? Or we're moving toward the light source, or we're moving away from the light source? Surely the speed of light has to depend on the motion of the light source or the motion of the receiver. And Maxwell's equation just says, don't know how to help you, the speed is the speed. So it seemed to physicists that there needed to be a fix, and in order to come up with the fix, they measured the speed of light under all kinds of circumstances. Moving toward us, moving away from us. When they did that with experiments on Earth, they always seemed to get the same speed of light. So then they said, oh, we need a faster speed. Well, the Earth is moving in its orbit, and we're seeing light from stars. So we'll measure the speed of light from stars, 6 months apart. So at one time of year we're moving toward a particular star, another time of year we're moving away from a particular star. We know our speed of motion around the sun. So they measured that and found speed of light was the same, whether we're moving toward a star or away from a star. This is very confusing. Physicists love Maxwell's equations. They want to believe Maxwell's equations, but they didn't know what to make of this speed of light being constant no matter what you do, independent of motion, relative motion. Einstein said, okay, we have a lot of evidence that the speed of light is a constant. Let's take that as a given. Let's take that as a universal result in the universe. And let's take that as more universal than the assumptions we've always made about position and time. This is very bold of Einstein to do, and he was very successful in showing that if the speed of light is a constant regardless of motion, then our understanding of time is wrong. Time and clocks are different than our everyday experience and different than we've assumed in physics and for all of history. Position, length, distance, yardsticks, those are different than we've always known. Length and time are different for observers that are moving relative to one another. It had not been observed. Einstein derived it from the speed of light being constant, independent of motion. Einstein showed that two events that we previously assumed were simultaneous, they are not necessarily simultaneous to observers moving relative to one another. One observer might find that event 1 occurred before event 2, and the other observer could find the opposite. Event 2 occurred before event 1. This is pretty hard for us to get our minds wrapped around, because we're in everyday life, the discrepancy is so small as to be immeasurable. If I'm moving in my car, my clock works the same as it does if my car is sitting in the driveway and I'm looking through my windows at my clock. If I have a yardstick, a meter stick, we don't see that it changes length with motion. But Einstein says, oh yes they do. Small but important changes. Einstein said, velocity is not what we think. If I see someone else moving at speed v1 relative to me, and they throw something at speed v2 relative to them, the speed of that object is not v1 plus v2 for me. It's a little different, but an important difference. Einstein said that mass is different than what we think. Momentum is different than what we think. Energy is different than what we think. This is a true revolution. It's very easy to get confused, very hard to think about it correctly. The math is not complicated, but our understanding of it is complicated. It's hard to believe. It's hard to understand. The same is going to be true of quantum mechanics. Quantum mechanics is true. We can do experiments. We can prove that things are true. But boy, it's hard to, we can do the math, but it's hard to understand the results. It's hard to believe them. So we have two revolutions, special relativity and quantum mechanics, that are really hard for us laymen to understand and believe. And yet, that is the universe. And we should want to try to understand that. Now, that's all well and good generally. It turns out we want a particular result from special relativity. We're going to need it for quantum mechanics. So we're going to pull out that result. For a particle traveling at the speed of light, which photons do, Einstein said energy is momentum. The energy of the particle is the momentum of the particle times the speed of light. Only for particles traveling at the speed of light. So the momentum is the energy divided by the speed of light. We already know from the photoelectric effect and black body radiation that for photons, energy is h times f, or h times c over lambda. So now we have, if we take momentum is energy over c, and energy is hc over lambda, then the momentum of a photon is Planck's constant over lambda, the wavelength, for a photon. We need this in quantum mechanics. We'll need it later, so we'll store that. It comes partly from the photoelectric effect and black body radiation, and partly from special relativity. That's really the only formula result we need from special relativity for ordinary quantum mechanics. But we need to understand when ordinary quantum mechanics is no longer true and sufficient, and we will talk about that. So photons possess momentum, And electromagnetic radiation exerts radiation pressure. We don't need it for quantum mechanics, but this is a convenient time to talk about electromagnetic radiation pressure, even though we don't need it for quantum mechanics. So you can skip ahead if you want, that's fine. This is a possible time to take a break. This is an image of a radiometer for observing radiation pressure. It's a vacuum-sealed bulb. It has an axis that can spin freely, not much friction or resistance to spinning. It has 4 vanes, and this 1, 2, 3, 4. In this case, they're squares and they're tilted, but it doesn't matter. They're usually squares, but they don't have to be. It's usually 4. They're usually 4 arranged in a cross. What's important is these squares, these vanes, they have 2 sides. One side is always black, and the other side is always reflective silver. They're not always oriented the same. You'll find other radiometers where this surface is black and this surface is silver, but always one is silver, one is black. There's where I got that image. So let's draw a picture. Ooh, I made it a little too big. Let's see if I can make it a little smaller. Okay. So this is a view looking from the top or the bottom of the radiometer. This black is the glass sphere. We have light coming from some direction, perpendicular to the axis, uniform light. It doesn't have to be monochromatic. I'm showing it all as red, doesn't have to be. It has some light intensity. We'll call that light intensity I. From the formula we just used, if we divide that by the speed of light, we'll get the radiation pressure. Here are the 4 vanes arranged in a cross. They can spin on the center axis. We'd like to know if they spin. So each vane has a silver side and a black side. So silver black, silver black, silver black, silver black. So here the silver side is facing the light, here the black side is facing the light, but it can spin. There will be a force, so the black side will absorb all the radiation, and so since the photons have momentum, the black surface is going to absorb all that momentum, and by conservation of momentum, it's going to have a force to its right. That force, due to the absorption of radiation, will be the intensity times the area of the vane, area A, divided by the speed of light. So radiation pressure times area of the vane is the force to the right on the lower vane, the black, with the black surface facing the radiation. Now the top vane, photons are going to hit the silver surface and they're going to reflect back because it's a silver reflective surface. So the pressure is going to be coming in, but the pressure is also going to get reflected back, and it turns out with conservation of momentum, the silver vane is going to experience twice the force as the black vane because it reflected all of the photons back away, and so it has to have twice the momentum to the right in order to conserve momentum. So there's going to be more force on the silver vein than the black vein. So there's going to be a net torque in this direction, and it should rotate. We're not going to care how fast it rotates, but it'll continue to rotate. You can buy these things for $10 new, and it for sure will rotate. Now, and so this is an example, an experiment that shows radiation pressure of light. The trouble is it's kind of it's a little bit of a flawed experiment because it works fine when you first get it, but over the decades, some air will diffuse through the glass, and so there could end up being not. And so this is the rotation that should happen if there was good vacuum inside the glass bulb. But if air has leaked through, there can be enough air pressure in here, small air pressure, but enough that these radiation forces, these radiation pressures, are not enough to cause it to move against the viscosity of the air. Worse than that, it can start to rotate in the wrong direction, in the other direction. Now, why is that? The silver surface still behaves the same way. The radiation pressure gets reflected, but the black surface, it's not only absorbing momentum of the photons, it's absorbing their energy, and it's slowly heating up over time. So this vein, the black vein, it gets to be hotter than the silver vein, and some of that heat heats up the air nearby. That air expands, and that expansion of the air pushes the black vein in this direction. So you might buy a second-hand radiometer at a garage sale, or you might have one old from when you were a kid, 30 years old, and you might shine light on it, and it shines in the wrong direction. And then you might come to believe that you understand how the thing works, but your understanding is wrong, because we're meant to understand how it works in vacuum, but if air gets in it, it behaves opposite. Now, for all the revolutionary aspect of special relativity that I've talked about so far, that was merely prelude to what Einstein wanted to get at, and the second part of his paper. Einstein wanted to know what happens to electric and magnetic fields in different inertial reference frames that are moving relative to one another. If I know the electric and magnetic field in my reference frame and someone else is moving relative to me, can I calculate what they see as the electric and magnetic fields? And he was able to calculate that, and that's successful. It's a correct result. And that was really important to him, and that's why he called his paper on the electrodynamics of moving bodies. Electrodynamics. It was important to him because Einstein wanted to know, what does electromagnetic radiation look like if he were chasing a light beam? Because of his interest in that, he revolutionized our understanding of space and time and energy and momentum, one result of which is that energy and mass can be interconverted. Particles can be created and destroyed in pairs. and we can get a lot of energy out of a small amount of mass, E equals mc squared. This is the basis for atomic bombs and hydrogen bombs, and also for the fusion that occurs in the sun and stars. So a lot of results from one paper from a 25-year-old who wanted to know what happens if I chase a light beam. This is a possible time to take a break. Now, why do we care about this from quantum mechanics? Mostly we don't, but mostly we can use ordinary non-relativistic quantum mechanics, the Schrödinger equation that we learn in as an undergrad in physics. We can use that to find the probable locations and momenta of a particle with mass, when the particle speed is much less than the speed of light. Or if we make some adjustments to the Hamiltonian, when the particle speed is maybe even a tenth or 2/10 of the speed of light. So one thing about quantum mechanics is about special relativity is it tells us, don't use ordinary quantum mechanics, don't use the Hamiltonian and the Schrödinger equation if the speed of a particle is faster than, say, 2/10 of the speed of light. Because that Schrödinger equation did not use special relativity. It used classical mechanics. It's valid, but it's not valid for relativistic speeds. For higher speeds, we need relativistic quantum mechanics. Sometimes goes by the acronym RQM. It's a graduate level course. It replaces the Schrödinger equation with the Dirac equation. It's harder to use than the Schrödinger equation, which is why we'll use ordinary non-relativistic quantum mechanics whenever that's applicable. But the Dirac equation is correct for particles traveling close to the speed of light, and we can learn that, we can use that. I have not yet taken my relativistic quantum mechanics course. However, life is not that simple that you replace the Schrödinger equation with the Dirac equation. Because when you get close to the speed of light, the energy of a particle with mass goes up with energy without limit, and it gets to points sufficient to spontaneously create new particle-antiparticle pairs from nothing, or from energy, or from vacuum, depending on how you want to think about it. It comes from energy, so they're not coming from nothing. The relativistic particle gives up some of its energy, and a particle-antiparticle pair gets created. Well, we need to include this effect for really high speeds, high energies. And in this regime, or if we want to get the highest possible accuracy for from experimental result, we need what's called quantum field theory, or QFT, a graduate level course. There are different quantum field theories that cover different situations. The one that handles electrons, positrons, which is the electron's antimatter particle. Same properties as the electron, but positive charge instead of negative charge. Photons, or any electromagnetic radiation. And the vacuum. The vacuum is not just nothingness in quantum field theory. It's very complicated. The theory that includes those particles and effects but no other particles, no protons, no neutrons, that quantum field theory is called quantum electrodynamics, or QED. It was developed by three separate people in 1946 to 1950. We're not going to be able to do quantum electrodynamics or quantum field theory or relativistic quantum mechanics, but we care about a result from quantum electrodynamics because it helps to prove that quantum mechanics is true and real. The electron has a property called the magnetic moment, which is like how much of a tiny magnet the electron is. That value is not a nice integer number. It's a messy number. It can be calculated from quantum electrodynamics using computer calculations. It can be calculated as accurately as you want, and there are experiments that can measure its value to 13 significant figures, and the experiments agree with the calculated result. This is the most successful result of any scientific theory or experiment. It's part of why we have to believe that quantum mechanics is true, even when we can't understand how it could be true or what it means. In quantum mechanics, we should look at quantum mechanical problems that produce an answer, a testable result that an experiment could check. We should do the experiment. That's how we should understand quantum mechanics. It's very hard to understand quantum mechanics philosophically, emotionally. What does it mean? What does it mean for life? What does it mean for the universe? What physicists can say is what it means for experiments. Now, a different quantum field theory is required to handle protons and neutrons. Protons and neutrons consist each of 3 quarks inside them and a huge sea of gluons, particles with no mass. Quarks have mass, gluons have no mass, like photons. A proton is a collection of its 3 quarks and a huge sea of gluons that remains confined to a small volume and behaves in many respects like a solid proton, even though it's not actually solid. There is a quantum field theory that describes how these quarks and gluons behave. It's called quantum chromodynamics, QCD. It was developed in the 1970s. It is much more difficult than quantum electrodynamics physically and mathematically, and to simulate on computers. The simulations require supercomputers, and they're not that accurate or detailed or refined. In almost all respects, physicists deal with what's called the standard model of particle physics, which is relatively easy to deal with, hard for us but easy for physicists to deal with, and is consistent with quantum electrodynamics, quantum chromodynamics, electroweak unification theory, as far as I know. So not every particle physicist necessarily takes a quantum chromodynamics course, because they deal with the standard model. They look for areas where the standard model is where there's a discrepancy with the standard model, and then quantum chromodynamics people might be involved to try and figure out how to resolve the discrepancy. But not every particle physicist takes quantum chromodynamics, as far as I know. Quantum mechanics and quantum field theories in principle, they're perfectly correct when there is no gravity. But there's gravity everywhere. There's gravity on Earth. How can we do experiments on Earth? We can't get around gravity. Going to the space station doesn't eliminate gravity. Yes, they're weightless because of their motion orbiting the Earth, but there's still gravity. And so quantum mechanics and quantum field theories, they're sufficiently correct for weak gravity. And luckily for us on Earth, our gravity is weak enough that quantum mechanics is correct. But they are definitely not enough, not sufficient, at the singularity of a black hole, inside the event horizon, nor the moment of the Big Bang. We do not have a testable theory of quantum gravity to go beyond quantum mechanics and quantum field theory and general relativity today. This is a possible time to take a break. Now, we're going to switch gears. I said we can use ordinary quantum mechanics when things are moving, less than the speed of light, like 1/10 of the speed of light or smaller. And if you're moving more than 2/10 of the speed of light, we need relativistic quantum mechanics. So maybe we should ask ourselves, how fast are we moving? How fast are the particles in your body moving? Maybe pause the video, take some time, think about it, do some calculations, see what you come up with. How fast are you moving? Well, your first answer is probably 0. I'm not moving. I'm sitting, I'm standing, I'm not moving. Well, okay, but you're on the Earth. The Earth is rotating. So we're moving with the Earth's rotation. Now, if you were at the scientific research station at the South Pole, you could say, no, not me, I'm not, and then you'd be right. But if you were at the equator, your speed is 1/millionth of the speed of light as you move with the Earth's spin. That's small. Not worried about it. The Earth is moving around the Sun 100 times faster, 1/10,000th of the speed of light. Okay. The Sun is orbiting the Milky Way 7 times faster. The Milky Way is orbiting our local cluster, and we're moving toward Virgo at 2/10 of the speed of light. So while you're sitting watching this video, you're moving at 2/10 of the speed of light and you didn't know it. We don't feel it, it has no effects. But we're cruising. How fast are the particles in your body moving? Well, a water molecule in water, it's moving because we have a temperature. We're not at absolute 0. I'm not sure of some of these results, my calculations, but I got that a water molecule might be moving at like 2/millionths of the speed of light. An electron in hydrogen's ground state, the electron in that hydrogen atom, actually not in that hydrogen atom, this would be electron in a hydrogen atom that is not bound, but that electron is moving less than 1% of the speed of light, 0.7% of the speed of light. So we can use ordinary quantum mechanics to do that calculation. But it turns out it turns out that value is higher for other atoms than hydrogen. I'll talk about that in a minute. We have potassium in our bodies. 0.01% of potassium atoms are an isotope that's radioactive, potassium-40. That has more than a 1 billion year half-life. You might say, oh, that's so long. Nothing's happening in my lifetime. But that's not true. There are so many potassium atoms in our body that even with 0.01% of them having a 1 billion year half-life, 3,000 to 4,000 potassium-40 atoms, nuclei, are decaying per second in our bodies. And that could be a small contribution toward, disrupting, ionizing and disrupting molecular bonds. Could be a small factor in our eventually getting cancer. The way that the potassium-40 nucleus principally decays is that one of the neutrons in the nucleus decays to become a proton, which makes the potassium-40 turn into calcium-40. In that neutron becoming a proton, it emits a beta minus particle, which is a high-speed electron, which can do damage in our body, and an antineutrino, which does no damage to our body. Now, potassium is also present in Earth's mantle, and its decays contribute to the heating of Earth's mantle, along with uranium and thorium. The electron that gets emitted when the neutron becomes a proton, it's traveling 0.08 times the speed of light. So, still could use ordinary quantum mechanics if we wanted to see how that electron interacts with some atom, how it scatters off some atom in the body. Now, we do have heavy atoms in our body. We have iodine in our body. Iodine is atomic number 53. It happens that the speed of inner core 1s electrons in atoms, the speed is generally proportional to atomic number. So the speed of a 1s electron in iodine is 53 times faster than in hydrogen. So 0.3 times the speed of light. So those electrons in iodine in our body, they're traveling 3/10 of the speed of light. Ordinary quantum mechanics would need some adjusting, or we should use relativistic quantum mechanics if we wanted to calculate the energy level of the 1s electron in iodine. But that would also be complicated, and there would be other effects, repulsion of the electrons and other effects. So we would have to solve that numerically and approximately anyway. Now, in the protons and neutrons in the nuclei of our body, there are 3 quarks in a proton and 3 quarks in a neutron. And they are traveling around 0.99995 times the speed of light, always, constantly. We don't experience it, we don't perceive it, it has no effect on us. The energy of those quarks is relativistic. Their energy is much higher than their rest mass energy. If we wanted to understand how quarks in protons and neutrons move and behave, we would have to use relativistic quantum mechanics. And we would need to use quantum chromodynamics to understand how they interact with the gluons in protons and neutrons. Now, is that the fastest thing that occur in our body? Turns out it's not. Cosmic rays are hitting our body all throughout our life, unless we go into a deep mine. But the cosmic rays have the highest energy when we're flying on a jet. Their speed is at least 0.999999999 speed of light. And it can be so high as to be 24 nines. These cosmic rays do damage our cells. Aircrew, pilots, and flight attendants have higher risk for certain cancers than ordinary people because of how much they fly. Living on the space station is an increased cancer risk, although they typically only spend a year or less there. Flying to Mars would have a cancer risk. Living or working on the surface of the Moon or Mars would have a cancer risk. You can shield to some extent, but the best shielding is to live and work underground. There also are neutrinos. They come from radioactive decays. They come from nuclear fusion in the sun and stars. They come from different areas of our universe. Solar neutrinos have 0.139s. There are higher energy neutrinos with many more nines than that. They have zero effect on our body. They just don't interact with our body. It takes very difficult and precise measurements to even measure them on Earth, and they have no effect on our body. Of particles with mass, neutrinos and cosmic rays are the highest speed, highest velocity particles that can be in our body. But we also have particles with zero mass, zero rest mass, in our bodies. The gluons in protons and neutrons, they travel exactly the speed of light. In vacuum, the space between quarks in a proton and neutron is vacuum. Photons travel at the speed of light in vacuum, but our body is not vacuum as far as photons are concerned. So they travel a little slower than the speed of vacuum in our bodies. They travel at the speed of water or the speed of air. I mean, the speed of light in water or the speed of light in air in our bodies. So actually a little slower than the speed of light in vacuum. This is the end of session B2.